KMP. It's a string matching algorithm. I just want to quickly come up with the problem. The string searching algorithm. Actually, we already used it. One of them it is being called Robin card algorithm. They apply for string matching algorithm, but it is a little bit. Actually, he's using the hash function. So actually, they're using the hash function to hash rolling matching approach to implement this string matching algorithm. And in today's oh, by the way, at that time, Robin Carp string algorithm actually the best, and then worst cases n m plus m complexity, and then there is a which is better than naive searching algorithm, which is brute force algorithm, n multiply m time complexity. What does means n is size of the whole context, which is that whole letter or book or article. M it is which is you're targeting the sentence. For example, you're trying to find a sentence in the book, or trying to find a word in the book. Then how much time appeared or where they appear, that's they trying to use it. Of course, this is one. Another is what, of course, the application should be trying to find plagiarism problem, right? If there is a you copied, cheated from somewhere else, then you needed to how much similarity in between the two articles. So that's a real application used the string searching algorithm. And then today's we are going to introduce another algorithm being called the KMP algorithm. KMP string algorithm that actually they will be get same performance, m plus n complexity. As I said, n is size of the whole context. M is size of the which is targeting the word or sentence. So if I mean there is a result is time complexity similar with same as m plus o n plus n time complexity, which is now similarly if linear, right? If it is small size of m, then it is linear. It's approximately linear time complexity, which is not bad. Another naive stock algorithm, actually they will be not naive string algorithms actually brute forces n multiply n time this is quadratic time complexity. So it is bad one. We try to improve performance. There is another option, so that's the reason we are going to learn KMP algorithm, and then KMP is another option to we can use the searching algorithm, which is because they give them better result m plus n time complexity, on plus n time complexity. Okay, so let's start from the problem, right? So KMP is there is a things. Okay, let's before I'm ordered to explain what the KMP is. Probably you didn't really much to understand if I'm directly introducing the algorithm itself. But first of all, I'm going to introduce the one algorithm being called naive algorithm, which is brute force algorithm. The performance is n multiply n time, so which is not we expected. So that's we are going to introduce. Then we can able to compare. Okay, that's the bad one. Then where is a good one is we can able to use it. So that's second reason solution we have KMP algorithm coming from. Okay, so what's let's say first of all the case that which is we not like it. This is quadratic time complexity m multiply n time complexity algorithm naive algorithm. Why we introducing that? Because which is that very easy to understand. I mean simple, straightforward, solve the problem. So it's easier to investigate the problem. So we can use it Navier-Stokes algorithm, naive algorithm. What's the feature is actually you take this the compared character pattern search in text. If you found it, you can find the pointer. Otherwise, you keep comparing with all of them. Each time you if you can find the reset the process, then repeat again. So that's naive algorithm. So how's look like? I mean, actually, there is you can see that the algorithm itself, T is text, P is pattern, which is pattern is trying. This is target. This is a whole text. I mean, there is a 1-4 from start to end. Yeah, so there is a if there is a matching, then found. Otherwise, you will be keep comparing it. That each time start from 0, repeat again. So that's yeah, force. The problem is, for example, let's say this is text and patterns test. This is a test text. Then what they're doing actually, they will define this output, but what they're trying to find is you know, they will be compare test 3 times, then I mean TST, I mean T is same, E is not, but they will be compared the 4 times. Then after that they already compared this one, then still they will be move again. Each letter will be and then 4 times comparison going to 0. So it means this is a if this is a, for example, how much this should be is probably 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 18 19 18 19 20 it is 20 letter include the space. So what is doing is actually there is a target is 4 what they start from the beginning to end. If you can't find, I mean, if there's not the text, then what they're doing is actually they will be going to compare 20 multiplied 40 times, which is that 80 times. That's the whole process of the comparing process. What does means is that's n size of n, that's m multiply n times what does means is kind of quadratic time complexity, which is we don't like it, but nevertheless it's very straightforward.
Sorry, teacher, your microphone is off.
I'm sorry, I talked too much. Okay, I'm back. Okay, so um okay, sorry, I think I should start from beginning. So what's the problem is actually we learned one of the algorithm before, which is Robin Cart algorithm, which is also applied for string search algorithm. That approach compared to brute force approach better. They will be provide n plus n time complexity, but here using the hash function approach. Today's there is another option using for string searching algorithm, but they will be gain also same as n plus n time complexity. There is another option, good algorithm for searching algorithm. But in order to understand the KMP, we are going to introduce the simple algorithm which is used to, simple understandable algorithm which is naive algorithm, but it is not efficient. As you can see, let's explain this article. First of all, there is the algorithm itself is simple. It can be understood straightforward. That's no problem. But the problem is he's not efficient. He's for example, let's say the whole string size is n, and the pattern strings, target strings m, then the whole cost of algorithm efficiency is n multiply n times. So which is that if m size very close to m, it means quadratic time complexity. It is not good performance. As far as I know, this quadratic is not a good algorithm performance. So the next question, do any kind of better algorithm exist? Yes, it is. One of them is KMP, another is Robin Carp, right? Robin Carp we already introduced yesterday, but today we are introducing KMP. It's totally different kind of approach. Robin Carp using hash function, but we're using the hash function also has problem with hash collision problem. So there is any kind of other better algorithm? Yes, which is like KMP. KMP's gain the m plus n time complexity, which is that if plus, it means this approximately both. This approach is linear time complexity. It's better than quadratic times, way more better than quadratic times, right? So assume that you have 100 letter, and inside you're trying to find five lengths of the size of the word. Then if doesn't exist, what they're doing naive stock is actually 5 multiply 100. It's 500 times complexity. But if I using the KMP, they will be n plus n, which is that 105 times complexity, which is very efficient linear time complexity. That's we expected. That's good one. And then okay, so that's to comparison. Now, what's exactly the naive algorithm work? Actually, naive algorithm is they will be keep comparing. Let me just introduce this one. For example, this AABA, they will be find this one, right? So it is a index, right? 15 letter. So what they're doing is actually A compared A, B second letter. They compared, actually they found it. So after that, this is first time appeared. Then of course, whatever each time they will be, for example, second times they will be just moving one index. They will be compared A to A, then B to A, the A to A, and then A to A. But this is in the second place already didn't match. It means it doesn't match. If doesn't match, they will be just moving one word. It is start from again this second index. They're going to compare A to A, B to A to B. Of course, doesn't match, but they will be complete this 4 time the comparison. Then, so it means this is kind of, it is a stupid comparison because we already know it. This is second time comparison is already doesn't match. You don't need to compare again. But the brute forces, they will be keep comparing. That's the reason that's stupid. But they can able to find it, right? So we trying to do is naive. Okay, we're trying to understand why is the naive stock algorithm it's not efficient. What they're doing is, for example, it is a pattern. This is a whole text, right? This is a pattern size M, text size N. What they're doing is, okay, you can see there is a 1 4, there's another 4. So they're trying to start from the I, right? Then they will be come to M. Let's say this way. If it's not doesn't match, they will be just keep continuing. If it is match, they will be find out what the index is. But they will be have to be does they didn't does match. They will be, I mean, for example, start from the J to M, increasing the, for example, here's let's say this, in this case, this 4 time, right? So this is a loop is 4 time. Then again start from the when they finished this 4, then come back to again to continue. It means for example 1 index, I mean it's I is, no, hold on a second, is N minus M. N minus M, that's fine, but they will be N is for example, let's say 100. So to start from the 0, they will be compared to 1 to 1. So for example, I is 1, right? I is 0 0 1, right? So let's say this is a 0, this is 0 0 to this is a I mean start from the J's. What's the J start from? I think J is 0, I is 0, right? So it means this is a 0 0 and this is 0. The first one is match. Okay, just keep moving. Does match, then keep moving. Second is does match, keep moving, keep moving, keep moving. But this is then, I mean, that's M multiply N times. So that's the reason quadratic time complexity, right? So it's naive stock algorithm is using that algorithm. But how's the, I mean, which is quadratic time complexity, and then KMP is N plus N time, which is linear time, which is we like it better than quadratic times. How's the KMP is working? Actually, KMP is trying to avoid the problem of the naive algorithm. Naive algorithm, they will be whatever they didn't match, they still reset back to compare again at the beginning. So it's not the good things. For example, A, this is first. Then when they compare to B, also same. But for example, let me just compare this one. For example, this one, AB, AB, AC. I mean, AB is same, but AB is same, but after that BA, not same. In the fifth position, not same. What they start is, so they will be just ignored the first 2 of them. They start from the, start from the AB. I mean, this already appeared that, I mean, they will go back to AB again. They will be, so they didn't reset back the previous one. Actually, they will be reset back, which is that second time appear, which is a little bit bad, a little bit good. So that's the reason KMP is O N plus M, N plus M time complexity. And here's a, so there's actually the algorithm itself, there's been called, there has some preprocessing existed. Let me just explain what's the preprocessing algorithm. There is a one things you needed to make it, which is they trying to identify how many time of, for example, the suffix prefix matching string existed. So what that means is if there is a whole text, if there is existed something something more appearable letter, which is being called last most pattern suffix or most pattern prefix. Suffix or prefix. So if there is a same letter appeared in many places, which is that what we going to pattern it. So the algorithm itself, at the first, each of them is initialized as a 0. Then if it is the if it is 0, it doesn't matches, doesn't change, so it is always 0. If it is matched, they will be +1. Doesn't match is -1. As you can see, there is a process. This is 0 0 position. It's this one, and this 0 is always 0. At the first, just mode 1. Second is compare this two match, then plus add 1. Store the value in the LPS and keep continuing. Then of course there is a current position is L is 1. That one is also same. And the secondary recursive is also match, then keep continuing. If there is a doesn't match, they will be -1 to save the value. If there is a less than, if there is a equal to 0, then they will be reset back to 0. So that's the algorithm itself. So that's a little bit more. This one, I think let's go to the more. I think that one should be better article, which is explained visually. Let's say this one. Okay. So actually, the KMP algorithm, they actually include 3 parts. One is the target, another is the pattern, third one is a last pattern suffix. The LPS is they're trying to create the LPS table. So based on that, they will be going to try to avoid the repeat the comparison process. So that's the reason of the KMP is much more efficient. How they was working? Let's say let's explain several examples. Let's say actually we have some example. For example, okay, I forget. This naive algorithm. For example, A B C D E F G H. Then we're trying to find DEF. DEF, it is in the index from the 4, 5, 6. What they're doing is actually what they compared is this is I, this is J. They compared A to D, and then E to B, E F to C doesn't match, so they're going to move D to B, E to C, F to D. Just like the 1 by 1, so which is very not efficient. So it's 8 size of 8. This is 3. Actually, the time complexity is m multiply. 8 multiply 3 is 24 times complexity. And then this is also the same thing. They will be compared to similar things. That's not efficient. And what the KMP is doing is, as you can see, for example, first of all they need to create the LPS table. Last appearable substring. So it means, for example, here's a let's say they're trying to find letter. For example, A B C D. And the same letter they trunk to A, B, C, D. There's also there doesn't exist, each of them is individual, didn't appear, so they will be always the 0. Then but A's appeared before, so that reason is 1. B also appeared before, that reason increased another 1. But after that, E is not appeared before, so that is 0. A's again, because they start appear again, so it's A. If because this is already in the A position, already been reset the position, so that's the reason 0. A is 1, B is 2. Then again, F is doesn't appear before, so that's the reason reset back to 0. So that's a kind of table. But and the second case is A, B, C, D, E. A, B, C, D, E is it's never repeated before, so that's first time 0. Then A is appeared before, so that's 1. B's appeared again 2. F is first time 0. A is before, they has 1. B is also, and C appeared also same, so that's 1 to 3. And then this case is A is 0, and then A appear again 1. B is first time, C is first time, A is appeared before, so that's 1. D is not, this is first time. A is before, D has before 1, and then this also A is second time. B, hold on. Actually, it's B should be 1. No, actually B should be 3, because B is appeared before. All right. So then 4 cases, A is second time appear, A is third time, this is a fourth time, so 1 to 3. And then B is first time, A is first, after then reset is again, C is 0. D is 0. Of course, C is not appeared before, D is also not appeared before, that reason. So that's how the LPS being created. Okay, so so when they when they create, you can able to create this the LPS table. Then you needed to, for example, they will be compared. As long as they does match, they will be check it this index. They will be returned back. For example, this one is was definitely returned back in the first position, but this one is not go back to first position. Actually start from the first position. This one's actually start from the third position, not start from 0. So it means only would save time. That's good. Now here's the mapping. Mean text is 1 1 1 1 3 1 1 1 3, and the pattern is 1 1 1. So beginning by comparing 1 1 1. Okay. So then after that they will be compare again. This execute the same amount of time the naives the algorithm. However, when they move on the second Windows pattern, so since already now the first 3 letter we had to check if the character last letters window from main text matches last patterns. So it means they already compared before, we don't need to compare again. Then they will be start from the 5th position, right? So that's good. I mean, here's another example. Let's say a 3. They trying to find. Okay, this is a 1 2 3. That's already found it. Last appearable suffix. What they actually doing is there is a suffix. A is also first of 0. A is both appear in the prefix and suffix AA. Length of 1. So this is 1. AA is also both appeared prefix and suffix AA, so length is 2, so it's 2. I mean, how they created 1 0 1 2 3. That's we already explained. Pattern A B C D is 0 because how they didn't repeat again. So that's always just there's always new things they going to compare it. That one's A's its second A's appeared once, B is first time, A is second time, A is again second time. So that's it's again. So this one, but C is first time. That's the reason the reset back. Then A B, of course, as well as A. So A B A is that's the reason they keep continuing, because there is a matching process existed, kind of, so that's they create this such kind of LPS. Why is increasing, right? So that's explanation how they created from 1 0 1 0 0 1 0 1 0 1 2, and then after that y is 1 2 3 4 5 6, because as long as didn't appear first time, they will be as long as they didn't reset back, they will be keep continuing growing. How does the algorithm work? Okay, KMP is, first of all, you need to input the text, input the pattern. They're trying to find this pattern is found it, the size. So they will be start from the J's, position of the current character, keys, position of the current character in the mapping, LPS, the longest proper prefix and suffix array. So that's a kind of algorithm. While J is smaller than text length, they will be keep continue. So get patterns, then text, they will be compared. Then based on the LPS table, they will be just move forward where we next times where needed to start from the compare with that. So that's the reason KMPs saved much more time than other algorithm, much more time than naive algorithm itself. Let's after that, I think we also needed to explain. Let's just explain this code. So how's compute PMP? I mean, that's a pattern, that's a size of the M, that's a LPS table. How's the KMP search, right? So actually, those you get the N and M. That's function here, as you can see. At the first, both are 0. Then while M is bigger than N, then they're going to compare this pattern, this length of the len is, of course, start from 0. So it is the both are increased, but they will be keep it. They will be, if it is same, then they will be update this value of the last appearable suffix. As you can see, they increased it, then put this in the LPS. Otherwise, if it's not the same, it means it's not 0. Then they will be decrease, right? Decrease 1. If it is if len is 0, then they will reset back. I mean, they already compared, and each time recursively compare with whether this existed, or that's the reason they becoming the 0. The len is 0, then that's the reason LPS become rest to 0, initial value. Then they will be continue to compare this process. In the result, they will be actually the save time of the comparison with comparison with the pattern latter. If doesn't match, they will keep moving. Otherwise, just go back to last appear suffix to get the index, not reset back to initial value instead of based on the most appearable position, so they will be save time. So this is KMP algorithm itself. So if you're interested, just try to run it, try to understand it. Yeah, we can discuss it. So basically, so there's a three important aspect. One is a text itself, another pattern, third one is the LPS. So you need to keep compare the LPS. While you compare the LPS, if you don't need to reset back the previous, you don't necessary to, there is a picture. Any picture, right? What's the KMP algorithm itself? Actually, they don't. If there has a LPS, then they don't need to reset back the whole length. You don't need to compare to start from the beginning. Actually, they based on the index to which is next pattern they're going to compare. So that's yeah, good things. They will be save time. All right, so there's another article also compared, and last one is, of course, there's a many algorithm. So you needed to understand how the time complex to. Robin Carp is O n plus n. KMP is also same, n plus n. Brute forces, which is naive algorithms, n multiply n. So yeah, we have two options. We learned before yesterday this one, and today's we learning the KMP. Okay. There is another article. If you're interested, you can compare with. You can continue to enhance your knowledge. There's exists the KMP or other algorithm, as well as there's one article compared to another with whereas string matching algorithm. It is not too old. They published 2015, so which is good. Then you can able to maybe try to enhance. You reference this algorithm. You can see that they will be compared actually several algorithms included KMP, but there doesn't exist Robin Carp. I don't know why. Okay, so that's all of the lesson for today. For application, actually, the string searching algorithm, they can widely used to bioinformatics, DNA sequencing, plagiarism checking. Actually, we always use all the time. All right. I think that's it. So again, I just want to summarize again. Today we learned another option to string searching algorithm. Another option, which means after that Robin Carp algorithm. Robin Carp algorithm is actually using the hash function approach, but this one is not using hash function. But they can get same performance, which is we expected, linear time complex, which is n plus n time. But do you think there is a worse than that? Of course, there has, which is that brute force approach, being called the naive string algorithm. This is quadratic time complexity. Then, if you understand what's the quadratic naive algorithm, then you understand that KMP is better algorithm than that. KMP is same performance with Robin Carp. KMP is, you can say that O n plus n, but brute force is n multiply n time. So that's the main idea of the algorithm. If you're interested how to implement it, there is a several code you can run for it. I mean, not only the brute force as well as naive algorithm as well. For example, there's naive algorithm, then you can run this one, then compare with the KMP. You can increase the data set, then you can able to understand which one is better. Okay, so I hope you have get a little bit make sense of the algorithm for searching string, checking plagiarism, or DNA searching bioinformatics. So that should be useful to applying such such application for learning. Okay. Any question, please?